This example problem looks something like a roller coaster. And what we're going to have to do is figure out some different velocities. We also have to figure out a height of some different points. So you'll notice in here I give you point A, point B, point C, point D. I give you the height at point A, I give you the height at point C. Also point B, we're going to say is at the ground level, so we know the height right there. We don't know the height at D. The one other thing we know is the velocity of whatever object we have. So let's just say it's a ball. So the velocity of this ball is 3 meters per second to the right at point A. You'll notice that the one thing I don't give you in this problem is the mass, because I wanted to show you how you can solve these energy problems with just looking at some of the variables and some of the different equations without having to know all the specific values at every single point. So the first thing I'm going to do is I'm just going to label the different energies that we have at point A, B, C, and D. Now, the one thing to consider is that in this problem we don't have any spring involved. Since we don't have a spring, I'm not going to worry about the spring potential energy. I'm only going to look at gravitational potential energy, kinetic energy, and then the total energy. So at point A, I'm just going to label kinetic energy, gravitational potential, and then my total energy. And then I'm going to fill in what I have. Same thing at point B. I'm going to label my kinetic energy, my gravitational potential, and my total energy at point B. At point C, same thing. Kinetic energy, gravitational potential energy, my total energy. And then at point D, kinetic energy, gravitational potential energy, and my total energy. Now, I'm going to start out at point A, because I know at point A, it has a height, it has a velocity, and I know both of those. So I'm going to use what I have here to fill in what I know. So the kinetic energy is 1/2 mv squared. Well, I know that the velocity is 3, so I know that the kinetic energy is 1/2 times the mass times 3 meters per second squared. I don't know the mass, so I can't really do anything else with that. I know the gravitational potential energy is the mass times the acceleration, which is 9.8 meters per second squared, times the height, which is 18 meters. Then I know that the total energy is going to be the sum of these two energies. So I'm just going to calculate what a value is going to be using that variable m there. So if I do 0.5 times 3 squared, I'm going to get 4.5 m for my kinetic energy. If I multiply 9.8 times 18, I'm going to get 176.4 m for my gravitational potential. So if I add those together, I get a total of 180.9 m. So 180.9 times whatever the mass of this object is going to be. Now that's helpful because I know that's the same at every other point. So at B, the total energy is 180.9 m. At point C, I know it's 180.9 m. At point D, I know it's 180.9 times m. So it's really important to understand the law of conservation of energy because that total energy remains the same. Whether I know the actual value or if I just know the equation, it's going to help either way. So now the next thing I'm going to do is look at point B. At point B, it's at the bottom. So I know that there's no joules of gravitational potential energy. That means that the kinetic energy is just 1/2 times m times v squared. But I know that the total, 1/2 times m times v squared, plus 0 joules, the gravitational energy, is equal to the total energy. So if I set up this equation, I know 1/2 mv squared equals 180.9 m, because I don't have to worry about plus 0, which means that the mass cancels out. So that means that 1/2 v squared equals 180.9 joules. So I can actually figure this out then just by taking 180.9 times 2 and then take the square root of that. And that's going to give me my velocity at that point, which is 19.021 meters per second. So even without the mass, I was still able to figure out the velocity at that point. Now comes the next point. So point C. At point C, I know that the kinetic energy is 1/2 mv squared. I know the gravitational potential energy is going to be mass times 9.8 meters per second squared, the acceleration due to gravity, times the height. The height is 9 meters. So if I really wanted to set this up as an equation to figure out the velocity, I know that the kinetic energy plus the gravitational potential energy equals the total energy at that point. So 1/2 mv squared plus, if I combine, so 9.8 times 9 times m is going to give me 88.2 m. That equals 180.9 m. Well, again, I have mass in every term. So I have mass, mass, mass. I can cancel out the mass. So I can solve this. So I can just take 180.9, subtract 88.2 from there, and I have 1/2 v squared left equals 92.7 joules, which means my velocity, it's not truly joules because it's actually joules divided by kilograms. I really should be careful about that. Joules divided by kilograms, because it's the joules divided by the mass. So that's 92.7 joules over kilograms. But either way, if I multiply 92.7 times 2 and take the square root of that, I end up with 13.616 meters per second. It's less than it was at point B, which makes sense, because it's going back up the hill. It should have slowed down a little bit back up at the top of hill C. Then for D, at the very highest point that the ball reaches, at the very highest point that it reaches, it's no longer moving. It's going to come to a stop at that point. So I know there's no kinetic energy. The gravitational potential is just mass times 9.8 meters per second squared times h, which means the equation I would set up here for my conservation of energy is 0 plus m times 9.8 meters per second squared times h equals 190.m. So if I do that, basically I have m times 9.8 meters per second squared times h equals 180.9 m. Again, I can divide both sides by the mass, so that cancels out. So I have 9.8 meters per second squared times h equals 180.9 joules per kilogram. So if I just divide 180.9 divided by 9.8, I get the answer I'm looking for the height, which is 18.459 meters. So you notice the one thing I wanted to show you in this problem is that it really doesn't matter that you don't have the mass. You can still set up your conservation of energy equations using your variables. A lot of times the mass will cancel out. Not every single time. You've got to be careful, especially when you're dealing with springs. But in this case, the mass is going to cancel out, and we can still get the answers that we're looking for just by looking at the equations with the variables.